Alright, so buoyancy applications. Buoyancy has an important application in transportation. Ships are designed to float in all types of water regardless of the density of that water. So this is made possible by the Pimsleur line. This allows or shows us how heavy a ship can be loaded at different water conditions. So the marks on the left side indicate fresh water, and the marks on the right side are for salt water. So as you can see here, there are different types of lines, and they all represent different things, and they're indicated there by, we have TF there for tropical freshwater, F for freshwater, T for tropical saltwater, all of those sorts of things. And then the depiction on the lower right shows you what the implications of that is. All right. Hot air balloons is another place where we have buoyancy applications. So as the air inside the balloon is heated, it becomes less dense than the surrounding air. So the buoyant force of the air will push the hot air balloon upwards until the buoyant force equals the force of gravity. So there's a picture there of the Hindenburg. And the Hindenburg was actually filled with hydrogen, which is actually why it ended up exploding. And we'll get into that in more detail later. Compressibility. So when the force acts on a fluid, that fluid is under compression. So some fluids under compression will take up much smaller volumes. These fluids, like most gases, are compressible. Other fluids, like most liquids, will have almost the same volume, making them incompressible. In terms of the particle model of matter, the spaces between the particles, it explains why there is so much difference in compressibility between gases and liquids, because gases have so much more space in between their particles than liquids do. So when a force is applied to the particles, much more compression takes place in a gas because there's so much more room in between these particles. Pressure, again, is something that we looked at in our last unit. It is the amount of force applied to a given area. It is measured in pascals. 1 pascal equals a force of 1 Newton over an area of 1 meter squared, which is something that we know from, again, our last unit. So the more force applied in a given area, the greater the pressure. So for pressure calculations there, the formula to calculate pressure is P, or pressure, equals force over area. And here we have the same shortcut. There it's in a circle. In your notes it's in a triangle with the triangle method, as I talked about before. So you cover the unknown part of the formula to determine what you have to do. Keep in mind that most measurements of pressure is in kilopascals, where 1 kilopascal equals 1,000 pascals. And pressure can also be measured in newtons per centimeter squared. If we talk about Pascal's law again, which is something that we already know, so in the mid 1600s, Blaise Pascal studied an experiment with enclosed fluids. Through his experiments, he found that the force applied in an enclosed fluid system created pressure that was transmitted equally in all directions throughout the fluid. So Pascal's law states that an enclosed fluid transmits pressure equally in all directions. This law has very important applications. So for example, in the picture there, as water flows out of the container in the way illustrated here because of Pascal's law. The pressure of the water on the sides of the bottle is equal at the same depth because the water travels in the same distance outwards before landing. So the greater the depth, the greater the pressure. Pressure increases with depth, so the more water above the hole, the greater the pressure, so the farther the water will shoot out of the hole. And this ties all in to when we looked at adaptations with saltwater animals and how they had to be adapted to the greater depths if they lived deeper in the water, right? That was something that they needed to be adapted to. Not all animals could go that far down into the depth of the ocean because of the pressure. Next, we're going to talk about fluid technologies based on solubility.